Okay, so remember what a partition was. If you have a closed bounded interval A to B, what do we mean by a partition of that interval? Well, we mean a collection of points x0, x1, x2 up to xn, where x0 is exactly A and it is less than x1, x1 is less than x2, dot dot dot, xn minus 1 is less than xn, and the last xn is the right endpoint of the interval, which is B. And when you take a partition of an interval, it divides the interval into subintervals. So because we are picking n plus 1 partition points, it divides the interval into n subintervals, okay? And so you have n subintervals. The first subinterval is from x0 to x1. The second subinterval is from x1 up to x2. The third subinterval would be from x2 up to x3. Dot dot dot. The ith subinterval, interval number I, would be between xi minus 1 and xi, and dot dot dot, the last subinterval is between xn minus 1 and xn. The size of the partition is the number of subintervals, which is n, which is also 1 less than the number of partition points. And remember, the mesh is the largest of the lengths of the subintervals. Okay, it's the largest of the lengths of the subintervals. So, for example, the interval from 2 to 5, right? If I pick the partition 2, 3, 4, 5, you realize that the size of this partition is 3, right? Because there are 3 subintervals, or there are 4 partition points, so 1 less than that is 3. And then the mesh of this partition is 1, because each subinterval has length 1, so the largest length is also 1. If I look at the partition P2, then this is for the same interval from 2 to 5. We have 2, 2.5, 3, 3.24, 4.6, and 5. And in that case, the size is 6, because there are 7 partition points. And the mesh is 0.8, because that's the largest of the lengths of the subintervals, right? So the first subinterval has length 0.5, second subinterval has length 0.5, third one has length 0.2, the fourth one has 0.8, the length of the fifth one is 0.6, and the last one has length 0.4. Is everybody okay with that? And then we looked at the interval from 0 to 1, and we asked ourselves the following question. We want to find a partition of this interval so that the partition divides the interval into n subintervals having the same length. Okay? So because the length of the entire interval is 1, I am dividing the length into n subintervals, so the length of each subinterval would be 1 over n. And so by using that, we came up with the partition points for such a partition. So x0 is of course 0, and then x1 would be 1 over n, because we want the length of the first interval to be 1 over n. x2 would be 2 over n, because we want the length of the second interval to be 1 over n again, right? And so on. And at the end, the xn minus 1 is n minus 1 over n. And the last one is n over n, of course, which is 1. The ith subinterval here is I minus 1 times 1 over n, and I times 1 over n. That's the ith subinterval. And we did the same question with a different interval from 2 to 5. I have the interval from 2 to 5. I want to divide that interval. I want to find a partition that divides the interval from 2 to 5 into n subintervals having the same length. Okay, so because I am so what's the total length of this interval? That's 5 minus 2, which is 3. And because I am dividing that length into n subintervals having the same length, the length of each subinterval would be 3 divided by n. Okay, so once I know that the first partition point x0 is of course the left-hand point 2. Once I know that, I add the length 3 over n to it to get the second partition point. I add the length again to get the third partition point. I add the length again to get the fourth partition point, and so on. So the ith interval, for the ith subinterval, the points are 2 plus I minus 1 times 3 over n, and the right-hand point is 2 plus I times 3 over n, and you get the last subinterval as well. So that's the that's how we came up with that partition. We defined Riemann sums after that. So let's say I have the partition P of the interval from A to B. So I have a partition P which is x0 up to xn for this interval from A to B, and so I have these subintervals, right? In each subinterval, I am picking a sample point. So W1 is a point in the first subinterval. W2 is a point in the second subinterval. W3 is a point in the third subinterval. Wi is in the ith subinterval. Wn is in the nth subinterval, right? So I am picking sample points. I am picking one point from each subinterval. And then what am I doing? Well, then given a function which is defined on this interval from A to B, we are evaluating the function at each of these sample points, and we are multiplying them by the lengths of the subinterval. So W1 comes from the first subinterval. I evaluate the function at W1, multiply that by the length of the first subinterval. The length is denoted by delta x1. So when I write delta x1, that's the length of the first subinterval. F of W2, so W2 is from the second subinterval. I evaluate the function at that sample point, multiply by the length of that subinterval. Okay, and then plus I do the same thing for each of the subintervals. For the ith subinterval, evaluate F at Wi, multiply by the length of that subinterval delta xi. So I form a sum like this, and then in summation notation I can rewrite the sum as the sum I going from 1 up to n, f of Wi times delta xi, and this is known as the Riemann sum of f on that interval from A to B with respect to the partition P. Okay, so the Riemann sum will be different for different partitions, right? Riemann sum will be different for different partitions. I'll try to motivate why we look at Riemann sums in a bit. And so let's look at an example. Suppose I have the function f of x, which is x squared, and I am given the interval from -1 up to 1. So my a in this problem is -1, my b is +1. Okay, so I am picking a partition P of this interval. So what are the partition points I am picking here? The partition points that I am picking here is -1, 0, and 1. Is everybody clear? I am picking 3 partition points. -1, 0, and 1. Those are my partition points. So if those are my partition points, then what's the size of the partition? My partition points are -1, 0, and 1. So my size is what? 2. And then what's the mesh? Mesh is 1. So I am trying to form a sum, Riemann sum, for the function f with respect to this partition, I'm picking two sample points. So I'm picking negative half to be the sample point from the first subinterval. I am picking half to be the sample point from the second subinterval. Okay, so I evaluate the function at the sample points multiplied by the corresponding subinterval lengths of the subintervals. So I evaluate f at negative half multiplied by the length of the first subinterval, which is 1. I evaluate the function at the second sample point half multiplied by the corresponding length of the subinterval, multiplied by the length of the corresponding subinterval, which is 1 again. And then if I add them, I basically get a 1/4. Remember, the function f is what? X squared, right? The function f is x squared. So what is f of negative half? F of negative half is 1/4. F of half is 1/4. I add them, I get exactly half. So that's the Riemann sum. I am going to use when I wrote this definition of Riemann sums, I am going to use a notation here, okay, which is I am going to denote the Riemann sum by R F of P, okay? So when I write R F of P, I mean the Riemann sum of F with respect to the partition P, okay? So in our example, this is the Riemann sum of the function x squared with respect to the partition P. Is everybody clear? Now we can interpret the Riemann sum geometrically, okay? So let's see what does this quantity have, the Riemann sum, represents geometrically. So remember, so what's the graph of my function x squared between negative 1 and 1? Between negative 1 and 1, the graph of my function is the parabola, right? And that's so the green curve is the graph of the function f, right? Between negative 1 and 1. So think about what we did with the partition, with the Riemann sum. What we did is we took f of, we evaluated the function at f of negative half. So what is f of negative half geometrically? F of negative half is the height of the graph at negative half, right? You view that? F evaluated at negative half, that's the height of the graph at negative half. Same way, f of half is the height of the graph at half, right? Realize that? So what did we do? We multiplied that height with the length of the subinterval, right? So if I multiply the height of the curve at negative half with the length of the first subinterval, which is 1, what do I get? I get the area of the rectangle with height f of negative half, and the length is, or the height is f of negative half, and the width is 1, right? So f of negative half is this height here, right? F of negative half is the height of the graph at negative half, and then when I multiply by the length of the first subinterval, I get the area of the rectangle with height f of negative half and width 1, right? Same way, f of half is the height of the graph at half, and if I multiply that by the length of the second subinterval, which is 1, I get the area of the rectangle with height half, width 1, right? No, not height half. I mean, height is f of half, which is 1/4. So the Riemann sum in this example represents the sum of the areas of these two rectangles, right? The Riemann sum represents the sum of the areas of these rectangles. Am I making sense? So in some sense, this is an approximation to the area below the graph of f over the interval from negative 1 to 1. Am I making sense? This Riemann sum is an approximation of the area below the graph of the function over the interval from negative 1 to 1. Am I making sense? Alright, so that's one example. And then let's look at another example. Let's now suppose that I have the function f of x, which is x squared plus 1. And we are now looking at the interval from -2 to 2. Let's pick a partition here. The partition that I picked here is the following. The partition P is -2, -1, +1, and 2. How many partition points? 4. I am picking the partition to be -2, -1, +1, and 2. I have 4 partition points. How many subintervals do I have? 3. So the size is 3. The mesh is 2. Okay. Now, what's the so what would be the Riemann sum in this case? Well, I have to pick sample points first. So in this case, what I did is I picked the sample points in the following way. From the first subinterval, the first subinterval is between -1 and -2 and -1, right? From that first subinterval, I picked the sample point W1, and I picked W1 to be equal to -2. Okay, -2 is in the first subinterval, so I picked this first sample point to be -2. The second sample point is from the second subinterval, and the second sample point is 0. And the third sample point is 1. Is that clear? 1 belongs to the third subinterval. 1 also belongs to the second subinterval, right? 1 belongs to both the second and the third subintervals, right? So I am from the third subinterval, though, I am picking W3 to be 1. So what's the Riemann sum then? The Riemann sum in this case would be I evaluate the function f at the sample point -2 multiplied by the length of the corresponding subinterval, which is 1, plus I evaluate the function at the second sample point 0 multiplied by the length, which is what? 2, plus f of W3 is f of 1 multiplied by the length of the third subinterval, which is 1, right? And if I multiply them out, remember the function f is x squared plus 1, right? So what is f of -2? F of -2 is 5, right? What is f of 0? 1. And what is f of 1? 2. So you plug them in, you add them up, you get 9, okay? So that's the Riemann sum of this function on this interval with respect to the chosen partition, right? Remember, Riemann sum depends on what partition you picked and also what sample points you picked, okay? Now, geometrically, what does this Riemann sum represent? Well, the blue curve, that's the graph of this function between -2 to 2. Okay. So remember, what are our sample points? Remember our partition points. The partition points were -2. Remember, the partition points were -2. Partition points were -2, -1, 1, and 2, right? Those were the partition points. Now, for the first subinterval between -2 and -1, what did we get for the So what's the first term in the Riemann sum? The first term we evaluated the function at -2, and we multiplied by the length of this first subinterval, right? So notice, what does that mean? What is f of -2 here? F of -2 is the height of the graph at -2, right? So you're multiplying the height of the graph at -2 by the length of the subinterval between -2 and -1. So what do you get? You get the area of the rectangle that I highlighted with magenta color, right? I don't know, is it pink or magenta? I don't know. Between -1 and 1, right? Between -1 and 1, what did we do? We evaluated the function at what? 0. We evaluated the function at 0. We multiplied by the length of that subinterval. And f of 0 is the height of the graph at 0, right? So we are multiplying that height with the length of the subinterval. So that's going to give me the area of the rectangle with height equals to f of 0 and width equals to 2. And we did the same thing for the third subinterval as well. So what's the Riemann sum? Well, so the Riemann sum Rf of P, it represents the sum of the areas of these rectangles, right? The Riemann sum represents the total area of these rectangles, the total area of these rectangles. So again, you can think of the Riemann sum in this case as an approximation to the area below the graph of f over the interval from -2 to 2. Yeah.
We have to be on something called goods or final or whatever. Will we get to pick our own partition?
It'll be provided. Yep. So you will not be given the freedom to pick your own partition points. I mean the sample points, because then I'll have many different answers for many different people, and then grading wise it's hard to grade. Okay. It's not hard to grade. It's just that I have to look through every single one. Otherwise, I could just look at the final answer and see if it is wrong or right, and then look into it if there is any problem with it. But in any case, this will be provided. Okay. So generally speaking, what's the geometric interpretation of a Riemann sum? So let's look at that now. So let's suppose I have a function f, which is a continuous function on an interval from a to b, and let's just assume that f is non-negative. Okay, if f is non-negative, then the graph of f is going to lie above the x-axis, right? If the function f is a non-negative function. Okay, so let's say I have the interval from a to b, right? And I am picking a partition, x0, x1, x2. It's an arbitrary partition with size n and whatever the mesh is, right? So it's just an arbitrary partition of the interval from a to b. And then I want to see what does the Riemann sum represent geometrically. Okay. So remember what we are doing with the Riemann sum, right? What we are doing is that we have the first subinterval between x0 and x1, second subinterval between x1 and x2, the ith subinterval between xi minus 1 and xi, that's the ith subinterval, the last one is xn minus 1 and xn. How many subintervals do I have? I have n of them. How many sample points do I pick? I pick n sample points, right? So when I pick the W1 is my first sample point, right? So in the Riemann sum, what's the first term? In the Riemann sum, the first summand is f of W1 multiplied by delta x1, right? F of W1 is the height of the graph at W1, right? And delta x1 is the length of the subinterval, right? Length of the first subinterval. So when you multiply them, what do you get? You get the area. When you multiply them, you get this area here, right? You agree with that? You get the area of the rectangle with height f of W1 and width equals to the length of the first subinterval, right? You agree with that? F of the first summand represents the area of the highlighted rectangle. How about the second summand in my Riemann sum? What am I doing for the second summand? I am evaluating the function f at the sample point W2 and then multiplying that by the length of the second subinterval, right? So what am I getting? F of W2 is what? F of W2 is the height. So remember, this is right here. That's the height of the graph at W2, right? So f of W2, that's the height of the graph at W2, right? Height of the graph at W2 and then I am multiplying that by the width of the subinterval. So when you multiply the width with this height, you get the area of this rectangle. So I get the area of this rectangle here. So that's the second summand, right? The second summand of the Riemann sum. And you keep doing that. So just let me just say dot dot dot. When I come to the ith subinterval, right? What am I doing? I am evaluating the function at wi. So that's the height of the graph at wi. So you make a rectangle with height equals to f of wi, width equals to the length of that subinterval. And so what am I getting? So in this case, I am getting the area of this rectangle here. You guys agree with that? Again, what's the width of this ith rectangle? The width of this ith rectangle is the length of the ith subinterval, right? The width is the same as the length of the subinterval. So I get that. And finally, we do the same thing with the last subinterval, right? We do the same thing for the last subinterval. We make a rectangle with height equals to the height of the graph at wn, and then multiply that, and width equals to the width of the last subinterval. So I get all these rectangles, right? So each summand in the Riemann sum represents the area of a rectangle like this, right? So if I look at the total area of these rectangles, wouldn't you say that that's an approximation to the area below the graph of f above the interval from a to b? Would you agree with that? Notice that the more partition points I pick, the better approximation I'm going to get for the area below the curve. If my goal is to approximate the area below the curve above the interval from a to b, then I should be taking more and more partition points, which is going to make my rectangles what? Narrower and narrower, right? And then I'm going to get a better approximation of the area below the curve. Okay, so that's the geometric interpretation of the Riemann sums. Okay, am I making sense? In fact, that's one of the motivations why someone will look at the Riemann sum. Okay, because you're trying to approximate the area below the curve. Everybody's okay with that? So so one thing I want to say here though is that notice that, so I have the Riemann sum, I'm calling that Rf of p, denoting that by Rf of p. Notice that if I pick more and more partition points, what does it mean in terms of the mesh? If I am picking more and more partition points, what does it mean in terms of the mesh? The mesh is going to 0, right? The more partition points you pick, the smaller the lengths become, right? More partition points will mean less mesh, right? So as you pick more and more partition points, your mesh is going to get closer and closer to 0. And as your mesh gets closer and closer to 0, these rectangles are becoming narrower and narrower, and you're getting a better and better approximation of the area below the curve. So how do I define the area below the curve then? What should I define the area to be? Remember, you don't have you have the for the area of a triangle you have a formula, right? Area of a rectangle you have a formula. Area of a circle you have a rectangle, right? But how about a given function and the graph of a function, positive function? What's the area below that curve? How would you define that? Well, you define it to be the limit of the Riemann sums. Limit of the Riemann sum as the mesh goes to 0. Am I making sense? So the definition of the area below the curve above the interval from a to b is defined to be the limit of the Riemann sum as the mesh of the partition goes to 0. Is that making sense? Let me give you another motivation to why we consider Riemann sums. Let's think about a rod, okay, with varying density. Okay, you have a rod or a wire with varying density. So let's think about whatever the rod is. Let's say we can think of the rod as part of the number line. So it represents the number line from A to B. Okay. And so how do I approximate the mass? How do I approximate the mass of the rod? Am I making sense? I know, let's say I know the density of the rod at each point. So the density is varying, okay? The density is varying. How do I come up with the mass of the rod? So what would you do in order to approximate that? Well, let's divide the interval from A to B. Let's divide the rod into smaller pieces, like tiny pieces, right? If you divide, so let's think about n being very big, millions, right? N is very big. So you are dividing, partitioning the rod into tiny pieces, right? Am I making sense? And in each subinterval, you're picking W1 and you're looking at f of W1, right? F of W1 is the density of the rod at W1. Is that making sense? Now, you're multiplying f of W1 with delta x1, which is the length of the first subinterval, right? What does that represent? Can anyone tell me? F of W1 multiplied by delta x1. F of W1 is the density at W1. Delta x1 is the length of the first subinterval. What does that represent? It represents the mass of that tiny piece. Why? Remember I said it's varying density, right? So f of W1 is not the density at every point in that subinterval. But because the piece is so tiny, I can think of f of W1 to represent the average density of the rod over the first subinterval. Am I making sense? So remember, at each point the density could be different. F of W1 is not the density at every point in the first subinterval. However, because that part is so tiny, I can think of f of W1 as the average density of the part of the rod defined by the first subinterval, right? So if you multiply the average density by the length of that part, you get what? The mass, right? The mass of that rod. What is density? Remember, the definition of density is mass per unit length in this case. Mass per unit length in this case. But when you're talking about another object, maybe you're talking about mass per volume, unit of volume, mass per unit area, depending on what type of object you have. So in this case, density means mass per unit length. Okay. So when you multiply f of W1, that's the density, mass per unit length, multiplied by the length of that part, you get the total mass of that part. So the Riemann sum in this case represents what then? It's an approximation to the mass of the rod. Now, if you pick more and more partition points, right, you're getting tinier and tinier pieces, your approximation will get better and better, right? So the mass of this rod should be defined how? Well, we define the mass of the rod to be the limit of this Riemann sums as the mesh goes to zero. As the mesh goes to zero. Or as we pick bigger and bigger partitions, the Riemann sums will converge to a number, and that number is the mass of the rod. Am I making sense? Is everybody okay with that? You're going to do this type of things a lot in physics, for example. All right, so that's another motivation why we look at Riemann sums. You can think of work in physics, the concept of work, in terms of Riemann sums as well. Okay. All right, so once again, what do we do with Riemann sums? I want to now define the definite integral, okay? What do we mean by the definite integral of a function? over an interval from A to B. Let's pick a partition of the interval from A to B again. Arbitrary partition, x0, x1, x2, xn. And the ith subinterval is I minus 1 up to I, right? Sorry, xi minus 1 up to xi. That's the ith subinterval. So what's the Riemann sum again? The Riemann sum Rf of P is the sum f of wi times delta xi, right? In each subinterval, you pick a sample point, you evaluate the function at the sample point, multiply that by the length of the subinterval, right? So the first summand is what? The first summand is evaluate the function at the first sample point w1, multiply by the length of the first subinterval. Second summand is f of w2. You evaluate the function at the sample point w2, multiply by the length of that subinterval. And you keep doing that, you get the Riemann sum, right? So how do I define what's called the definite integral of the function? Well, it is basically this. Here I'm not assuming f is a positive function, okay? F could be whatever function it is. I am defining the definite integral of the function f on this interval from A to B, and it is denoted by this symbol, integral sine lower limit a, upper limit b, f of x dx. So this is this thing here. This thing here is one symbol, okay? And that symbol represents the definite integral of f on this interval from A to B. And what is that? Well, this is the limit of the Riemann sums of this function as the mesh goes to 0. Am I making sense? The idea is that if you pick more and more partition points, so that you are picking partitions with you're picking partitions where the mesh is going to 0, then the Riemann sums will converge to a number. And if it does converge to a number, we are calling that the definite integral. So the definite integral, once again, if you pick bigger and bigger partitions, if you pick partitions with more and more points, the Riemann sums will converge to a number. And if it does, I should say the Riemann sums may converge to a number. And if it does, then we call that the definite integral of the function on that interval. The Riemann sums may not converge to a number. Okay? In that case, we say that the definite integral does not exist. Okay? The definite integral is not defined. Am I making sense? Okay. So that's the definition of the definite integral. Is the limit of the Riemann sums as the mesh goes to 0, which also means as the size of the partition goes to infinity. Am I making sense? If the mesh goes to 0, it means you're picking more and more partition points, which means that the size of the partition is going to infinity, right? Is everybody okay? There are two special Riemann sums that I want you to know about. One is the left-hand Riemann sum. So remember, if I have a partition, I have to pick sample points, right? So what is the left-hand Riemann sum? ln of f. ln of f means you are going to evaluate the function. You are going to evaluate the function at the left endpoints of each subinterval. So you're picking the sample points to be the left end points of the subintervals. Am I making sense? So what is W1? W1 is x0. You're picking the left end point of the first subinterval to be the sample point. What is the second sample point, W2? You're picking W2. So W1 is I'm looking at ln of f. Okay, so let me use blue here. W1 is exactly x0. Okay, W2 is exactly x1. So you're picking the sample points to be the left-hand points of the subintervals. Is that clear? And then whatever the Riemann sum you get, that's called the left-hand Riemann sum with for this function with respect to this partition. And then instead of picking the sample points to be the left-hand points, left-hand points, I can pick the sample points to be the right-hand points of the subintervals. In that case, I call that Rn of f. Rn of f is the right-hand Riemann sum. And so in the second case, we are picking W1. We are picking. We are picking W1 to be x1 in the second case. We are picking W2 to be x2. And we're picking Wi to be xi. So we are picking the sample points to be the right-hand points of the subintervals. In that case, I get whatever the Riemann sum I obtain, that's the right-hand Riemann sum. Is everybody clear? Why am I looking at them? Well, if I know, remember we defined the definite integral from a to b of f of x dx. We defined that to be the limit of the Riemann sums as the mesh goes to 0. If the definite integral exists, right, it is defined as some sort of limit, right? So because it's some sort of limit, the limit may not exist, right? So, but if it exists, if I know that the definite integral is defined, then then it is equal to the limit of ln as n goes to infinity, or the limit of Rn as n goes to infinity. Am I making sense? So if you know that the definite integral exists, then you can find it by taking the limit of the left-hand Riemann sum ln, where n goes to infinity, or the right-hand Riemann sum Rn, where n goes to infinity. Not only that, when I defined ln and Rn, you can think of each subinterval to have the same length. So when you pick your partition of size n, you can just take the length of each subinterval to be the same. Am I making sense? So when I define ln and Rn, think of the lengths of the subintervals to be the same. Is everybody okay with that? All right. So that's how we define definite integrals. So what you want to do when you go home today, make sure you read through the notes again. Watch the video again if you have to, but make sure you understand how we are defining the definite integrals. I haven't talked about how to evaluate definite integrals. Okay, on Wednesday we will do just that. Is everybody clear? Everybody's clear? Okay.